We're just going to take a look at some examples here. Let's integrate the function e to the y squared. D will now be this region described by the set where y goes from 0 to 1 and x goes from 0 to y. This is what's called a type 2 region because the values of y are constant, but the values of x are functions. In all cases that we talk about when we do these double integrals, always draw a picture. In this particular case, we're integrating from 0 to 1 in the y direction, and now we want to take all the points that go from 0 to this line, y equals x. So the integration region lives in here, and what we're going to be doing is integrate in x first, then in the y direction. It's going to be helpful for us to think of how to set up these integration boundaries. This point lives at an x value of 0, and it has y value there, and this point lives here with this y coordinate there. In this particular case, the h1 function would be 0, the h2 of y would be y. When it comes to the integration limits, small x values going into large x values. Well, small x values live on the left, large x values live on the right. So this double integral over the region D becomes an integral where first we go from 0 to x, e to the y squared dx dy. Now note, this function e to the y squared, this is a constant with respect to x. That's really, really handy because there is no antiderivative formula for e to the y squared if we're integrating with respect to y. That sort of mindset will help us a little bit later on in other examples. So when it comes time to integrate this, we'll have an outer integral that we don't touch. This is going to be x e to the y squared evaluated from 0 to x. My apologies. This should be a 0 to y. So this should be a 0 to y. What we'll get is 0 to 1, y e to the y squared, subtract 0 e to the y squared. That goes to 0. As we expect when we calculate an iterated integral, everything should be in terms of the remaining variable. At this point, to evaluate it, we perform a substitution. U is y squared, du is 2y dy. If y is 0, that implies u is 0. If y is 1, this implies u is 1. We'll still get limits from 0 to 1, e to the u, du over 2. So at the end of the day, this will give me e to the u over 2, evaluated from 0 to 1, so e minus 1 over 2. If we had been given the region in the other way as a type 1, we would not have been able to integrate this because the antiderivative function doesn't exist for e to the y squared. As another example, let's talk about the integral of this function x plus y, where D is the region bounded by y equals x squared and y equals root x. So this is the curve y equals root x. This is the curve y equals x squared. The region of interest here is this shaded area. Now the intersection points here are going to be where x squared equals root x. So that's x squared minus x to the 1/2 is 0. If I take out that common factor, I'll have x to the 3 over 2 minus 1 is 0. This is a product that equals 0, so the solutions are either x is 0 or x is 1. Now the nice thing about this region here is that could be either type 1 or type 2. So we're going to try to talk about it in both ways. If it's a type 1 region, the x limits will be constant, and then the y limits will be variable. Essentially, what we're talking about is building some sort of slice that looks like this at some fixed x range. The lower curve is x squared, the upper curve is root x. So in this case, our limits of integration would go from 0 to 1, x squared y to root x. So if we wanted to evaluate this double integral over D, we'd have 0 to 1 as the outer integral because it's on the outside, it's the constant variable. On the inside, the lower limit is x squared, the upper limit is root x. We'll be integrating with respect to y and then x. It makes sense that the inner limits are in terms of x because that's the second variable. On the inner integral, y is the variable, so we'll get an antiderivative of xy plus y squared over 2 when we perform the partial integration. At this point, what we'll need to do is evaluate that inner term. So we'll have x root x plus root x squared over 2, subtract x times x squared plus x squared squared over 2. That's going to be integrated with respect to x. At the end of the day, what we'll have is x to the 3 halves, x over 2, minus x cubed, minus x to the 4 over 2. What we need to do is perform this basic anti-differentiation. X to the 5 over 2 divided by 5 over 2, x squared divided by 4, x to the 4 over 4, x to the 5 over 10, evaluated from 0 to 1, we'll get 2/5 plus 1/4 minus 1/4 minus 1/10. These two terms will cancel out. We'll have 4/10 minus 1/10 is 3/10. Now, at the same time, I could write this region as a type 2 region. That means the y limits are constant, and then the x limits are variable. Now, this curve right here was y equals root x, so x would be y squared. This curve, y equals x squared, so x would be root y. For some value here, this left is going to be y squared at some height y. This is going to be root y at some height y. So the integral over this area D, over this region D, y is the outer integral, x is the inner integral. So the smaller x value lives to the left, the larger x values live to the right. What we're going to have is exactly the same form of the integral that we encountered above. This integral is no different than what we had earlier. So we are going to get the same result of 3 over 10. Some integrals allow you to choose type 1 or 2, some don't. Sometimes we need to switch order in order to be able to evaluate this integral. So as our final example, the region of integration, x goes from 0 to 1, y goes from x squared to positive 1. So this would be a type 1 region. Here's the region that we've been given. And we're going from 0 to 1. And the y boundary is always above the parabola x squared, but always below the constant height of 1. As given, we are going to encounter a problem. The integration variable is y, and I now have to integrate sine of y cubed. There is no formula for the antiderivative, and that means I can't make any progress going forward. So what we're going to do here is switch the integration variable because I'm allowed to by Fubini's theorem, and that means I have to describe this as a type 2. Now I know that y is going to go from 0 to 1, but now I need to bound x between two functions. Well, on the left, x will always be greater than or equal to 0, so some point here has an address of 0 and y. This curve right here is y is x squared, so that means x is root y. So some point there would live at root y and y. And so now the integration variables are set. So the integral of this function over d can now be written where the y integral is outside. We'll have 0 to root y, x cubed, sine of y cubed, dx dy. And that means all of this is a constant. If I proceed from here, I'll get x to the 4 over 4 sine of y cubed, and this is going to be evaluated from 0 to root y, and then the answer will be in terms of y, and I'll have to integrate over x, 0 to 1 root y to the 4 over 4 sine of y cubed minus 0 dy. This ends up giving me an integral that's purely in terms of y's as I need. And very conveniently, this will be something that I can evaluate using a substitution. So u is y cubed, du is 3y squared dy. When y is 0, u will be 0. And when y is 1, u will be 1. This allows me to write the integral as follows. I can take out the 1/4, another 1/3 integral 0 to 1 sine of u du. What function do I differentiate to get sine? It's negative cos. This time evaluated from here, I'll get negative 1/12 cosine of 1 minus cosine of 0. This is going to end up giving me negative 1/12 cos of 1 minus 1. This integral could not have been evaluated in the order that was given, so sometimes you need to switch the order.